Today we're going to move on. We spoke about the formation of the planets and what the planets look like. They're all very beautiful. We've seen them all now. What we have not done is talk about the comets. A comet here. Now this is about the comet that struck. This is in Arizona, Barrington, Arizona, somewhere. Where the hell is this place? Somebody's been there. I don't know. It's in the middle of the map or something. This thing, the comet was estimated to be less than 10% the size of the crater. All right, and it had a classical impact. There's very little debris of the comet. But what there is a little bit of iron filings, iron pieces seen in the ground underneath it. Okay. Now that comet struck, we think, 50,000 years ago. All right. Now here is one way you can detect them. You're taking a plate. These are the star field, and you take a picture, and by God, an object moved during the time you took this plate. It probably was an hour-long exposure of the sky to bring it up, and in that hour, a little comet moved. That really means it's close to us, and because if it were moving at any speed and we're at the distance of a star, you'd never see it. But this is close to us, and it's moving in the foreground. Okay, in fact, here are other comets. Aren't they pretty? Now these are, they occupy a belt between Jupiter and Mars. The largest one is 940 kilometers, and there are 40,000 of them known. And 40,000 comets are known in this belt, and they total less than the mass of the Moon. Most of them are small and dark. The albedo, that's the fraction of sunlight reflected, is 5 to 10%. So mostly they absorb the light. They don't emit the light in the visible bands. This is what they look like. It looks like a nice potato. Here's another potato. And now here, this is kind of a neat system. This one, see that little moon? This is in orbit around this, this big thing. It spins around it, just like Kepler's laws tell you it will do. Okay? Spinning, going around it. There's no reason it can't happen. Now, it's not spinning very fast because the mass of this planet, of this comet, isn't very high. But nonetheless, it's pretty. Okay. So this shows you how comets are made. And look at all the junk chipped out of this thing. These comets have been in space for a while, and they've all suffered serious collisions, just like everything on the Earth. Okay. In fact, here is a map of the comets, 153,000 comets showing their position as of January 2004. Here is the main belt, and here is the orbit of Jupiter, and here is the orbit of Mars. The comets are, again, mostly, they're between Mars and Jupiter. Now, there's nothing that says the comets are going to be in nice orbits, that nothing ever happens to them. What would happen if two comets had a collision? Bang. And they chip off a piece of the comet. What orbit does that piece of the comet take? Well, pretty much the orbit is unspecified initially. Depends on the energies and what the impact parameter of the collisions were. But you can, from this, you can have a piece of the comet go in an orbit down close to Earth, or even within Earth, down to the Sun. So these comets can collide, and their collisions can be dangerous to us. All right, so we'll see about that later. Okay. Now, such a thing as known as meteorites is a chunk floating through the solar system, meteoroids. And they're in orbits that cross the Earth, some of them. Orbits that cross the Earth, that is, they go closer to the Sun than 1 astronomical unit, are called Apollo asteroids. Those are the objects that could hit us. All right, the others that orbit further out aren't going to hit us. Okay, they're very small, produced by collisions, as I said, and only the asteroids have a chance to hit us. Now, when they enter the atmosphere, that means they come within a radius of 100 kilometers for the surface of the Earth. They get to the atmosphere, and they start being dragged by the atmospheric molecules, much as the same as the drag that brought down the NASA station the other day. It landed in the Pacific Ocean. You all hear about that? Yeah, right? How many heard about it? Okay, this thing. Now, why was it difficult to calculate where it would go? It was difficult because the dragging force really depended on the profile that the satellite presented to the wind. After all, you know, when you go in a windy environment, if you're on a bike, you get down low so that you don't produce so much resistance, so much wind resistance, et cetera, et cetera. So you get in it, and they didn't know how the satellite was tumbling. If it tumbles at all, it makes it very difficult to calculate where it's going to, how much drag is being produced on the satellite. So it's never really obvious how to calculate where it's going to land. All right, now they burn due to friction, and they produce the lovely shooting stars you see at night. All right? You've all seen shooting stars, I presume. Anybody who hasn't seen shooting stars? Wow. Wow. What you have to do, here's an assignment I'd like you to do. Go someplace that's a little darker than Berkeley. Like, for example, even going out to Inspiration Point on eastern Berkeley. It doesn't have too many lights, and not as many as in Berkeley. You go out there, and you just take a blanket, stretch it out, and lie on your back, looking up at the sky. And just wait there 10 minutes, 10 or 15 minutes, for your eyes to dilate to the skylight. And then you will see magnificent, everything comes magnificent to see there, to see how many stars you can see. And finally, you'll see, bang, this way, that way. You'll see meteoroids burning up in the atmosphere. As they drag through the atmosphere, they get very hot and they burn up. Most of them burn up, but not everything. Okay, now a meteorite, a meteor, is a shooting star, and they're really not very big at all, size of pebbles. These are ice or rock, something from the solar system. Okay, a meteorite. These names are silly. You know, don't worry about the precise definition of names. I'm never going to ask you the precise definition of names. You know, that has nothing to do with exams in college. It may be important for high school, but believe me, you can look up the name to get the right one. I don't care about that. Meteorite, a meteorite, or whatever. Look it up. It's not important. It's never going to be a question on an exam. All right, it can hit the Earth. All right, and so they're called meteorites after it's hit the Earth. All right, such as the object that made the crater in Arizona. That was a meteorite. Okay, there are carbonaceous chondrites, are meteorites that are apparently made of complicated molecules. They have carbon in complex molecules, and there has been thought, now I don't know how this is very believable, there's been thought that these contain amino acids. They do contain amino acids that are seen in them. And they even said, well, you know, they're in an environment where they get ultraviolet bombardment from the sun and blah, blah, blah. Life forms on these meteorites, and then gets spread around the galaxy. That's ridiculous. But that's an idea that's out there. Look it up on Wikipedia, see what they say about them. But it's not a believable idea. I don't think you need that to make life. We'll see at the end of the course. We'll talk about that. Okay. Now, iron nickel are sometimes some of the meteorites are iron nickel composites, and those are heavy and they will erode slowly. I believe that the sacred stone of the Muslim community, the thing that has a mosque built around it in Saudi Arabia, what is this, in Medina? What the hell is that? Anybody know what I'm talking about? Mecca. Okay. That is a meteorite. All right. That is sacred. Okay. And some of them are clearly ejected from Mars or the Moon. We talked about one early in the course where a man found it in Antarctica, right, with a glove and all that. You know, it's cold there. So he was in Antarctica finding it. Okay. So the satellite we saw was oh, I'm sorry. Here, I want to show you this thing. This is a neat picture. All right, I'll get to that in a moment. All right, so comets are thought to come largely from a region that is known as the Oort cloud. Oort was the Dutch astronomer who worked on this all his life. He'd done a lot for galactic astronomy. He named them, and people now call them Oort clouds. The Oort cloud is really, really big, 50,000 times the distance of the Earth to the Sun. It's basically out in infinity. And they come in from they're orbiting extremely slowly, and occasionally they fall in. They're perturbed by stars, and they fall into the solar system, and then we can see them for the first time. The Kuiper belt was not discovered until recently, and it is just outside the orbit of Neptune. Here is the orbit of Neptune. The Kuiper belt is a cloud of comets in this region. Now here is this is a comet, a picture, and it has two tails. It has a plasma tail and a dust tail. And we'll talk about that later. Now, a blow-up, if you look at it closely, shows the comet, a big rocky mass, but containing lots of ices and other stuff like that. And the comet is blowing off lots of gases from the surface. Every time it comes into the solar system, it comes into the sun heats it up, and then it starts venting. Everything blows off. Okay, now the dust tail, the comet, you note the plasma tail is exactly opposite the direction to the sun. There's the sun up here, and the plasma tail is this way. All right, the comet is moving this way. Okay, so let's see what's going on. Oh, here's another comet. This is on the ice of Callisto. 1, 2, 3, 4, 5, 6, a whole bunch of skips. See that? Isn't that a beautiful crater chain? Have you ever been near a pond and you skip a stone? You throw a stone into the water, and you see how many times it will skip. 1, 2, 3. I've gotten up to 8 or something on a stone that I threw right, and it did very nicely. That's in the old days. Anybody can beat that record? 8? You never beat that record? Well, I practice. Okay, well, this comet apparently came in exactly right to skip tons of times. Bang, 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 bang. It skipped as it bounced along. Must have been exactly parallel to the surface of Callisto. It just banged all the time. Pretty crazy. Yeah. Anyhow, that's a record. I don't know what year that was. Probably 1 billion BC or something like that. All right. So now the comet, as it orbits the sun, the comets are in elliptical orbits, which are allowed in Newtonian mechanics. We didn't talk about the details, but the orbits that are allowed would be either circles or ellipses. Okay, and an ellipse, in this case, ellipse looks like this. Now, the comet here is the Earth's orbit here. The comet is on a circular orbit. Remember, it's slow out here, fast in here. The comet, when it's far away from the sun, is cold, of course. The sun doesn't heat it up so much, and that means that the ice doesn't evaporate off of it, and it doesn't have a tail. So the tail starts to grow when it gets closer to the sun. Here, its comet tail dies. And this tail points away from the sun, but here, now look at a case. It's got two tails, one plasma tail and the other dust tail. The plasma tail is reacting to the solar wind. The sun is putting out a constant stream of particles, charged particles, just throwing them out. And they are much like, it's a pressure, and they throw them out. And the plasma tail is reacting to the solar wind. And the wind pushes the tail back. So the other tail, the dust tail, is composed of heavier particles than individual atoms. A speck of dust won't be bent by, or isn't so badly pushed by, an individual photon or an individual atom. So it's dragging behind the comet. Here is this way, this way. Now note this, it's very important here. This comet has a tail here, but when it goes around, you see that even though it's going this way, you would think, just without thinking about it, you would think the tail goes behind it, but that's not right. The tail points away from the sun, every place on the orbit. So here it's going this way, yet the tail points in the forward direction, more or less the forward direction. Right? It does not point in the direction it came from. Remember, there's this out here, this region is just about a complete vacuum. So you don't have tails the way you would think you would in the air. Okay. Again, the ion tail goes behind, the dust tail is bent around. And the sun is down here. Here are some beautiful pictures of comets. Here is the ion tail, I guess. And here's the dust tail. All right? Okay. All right. Now, how many of you have seen comets, by the way? There haven't been any good ones lately. What did you think when the comet was there? How big was it? Sometimes comets have been 40 degrees in the sky. It was that we've seen comets that have been that big, fairly close. They came in big, and people when Halley's comet came around in earlier times, around for Mark Twain's death. Oh, by the way, Mark Twain said, "I was born with a comet." No, wait a minute. He didn't say that. But he was born and died on the intervals of Halley's comet, which is, the hell is that, 88 years?
75.
75? Yeah. Okay. So that was how long he lived, and that was the time his lifespan. All right. 75 years is the, yes?
It said, when I was in the book, it said that last time Halley's comet came, it was like twice the size of the moon, or something.
Twice the size of the moon? Well, are they talking about the size of the tail? Or the size? The comet wasn't that big. It'd be the tail they're referring to. And that's not that long. really a really good tail is much bigger than the half moon size. That's only half degree. Sometimes the comets are 10 degrees. They're really up there. Very impressive. But okay, that was Halley. Now they come back, and we'll see different sizes for it. We're 75 years doesn't guarantee that we're in the same place on the orbit as we were the last passage. We may be on the other side of the sun and may not be so dramatic at that point, etc. Okay, so that's an issue of a comet. Here is another picture. Very pretty, Hale-Bopp. Here are the two tails, very distinct. So this one is pointing back to the sun, over here. Okay. Here is Hale-Bopp again. Beautiful picture. See, it's about as big as a saguaro. There it is. And here he goes to M31, Andromeda. You see? This is the way to get to Andromeda. You hop on a comet, and off you go. So that beautiful pictures you can take. That is whatever the hell the name of it is. It's some name in Japanese name. Japanese have been good comet hunters, so they get the person who first sees the comet gets to name it. Okay, I don't know what that means. Anybody conversant in Japanese? Or is that a proper name? Sorry? Okay. All right. Okay, comets. Now, people didn't know what they were. They thought, in fact, that it was very dangerous to Earth if the Earth would go through the comet tail, and they sold prescriptions to take in case you ingested the atmosphere of the comet. This was at a day of lots of quack medicines in the early 1900s when Halley's Comet was around. They really didn't know what the hell was going on. They hadn't taken an Astro 10. Okay, so they were a long time ago. You see this in the sky and say, oh, that's an evil omen or something or other. All right, and basically a comet, you can think of a comet as a dirty snowball. And that's really what they are. Dirty snowball is the best way to think of it. And Halley's Comet, the comet that has been around every 75 years for a long time, I don't know, 10, it's been around, we've seen it 10 different times as it goes by. It has a constituency of coal dust, and that's, it looks like coal dust. Okay, very eccentric, okay. All right, just summarizing what I said. Comets, again, Kepler's second law applies, equal area in equal time. So in a month, it goes small area. If it's far away, it goes a big area. It goes large. It is moving faster when it's closer to the sun, slower when it's further from the sun, according to the second law. Okay. The issue of how often we see comets is very touchy. It's not clear. You can't see them very often, so we don't know. But what is said, if you have a cloud around us of 50,000 astronomical units, and you have a star passing through it, or near it, or somewhere nearby, it can perturb the orbits of those comets. It'll shake them a little bit, and then the comets, with this shake, will take an orbit that falls into the sun, and they may or may not fill what is known as a loss cone of comets that fall into the sun. Now, one question is, why are they out so far? Why are they out so far? The thought is that they were kicked out there by the giant planets in our solar system. Jupiter and Saturn kicked the comets out in the same way we saw that it can kick out a comet that comes near it. And they kicked them pretty hard. That's about as far out as they can be and still be attached to the sun. Okay. Now, there are comet showers, or not comets, meteor showers, excuse me. Meteor showers are known to occur when the Earth passes through the orbit of an old ancient comet. You've got old comets, you knew where they were. The Earth has an orbit that we know where it is, and the Earth passes through it. And along the comet, the old comet, is a trail of dust. And this trail of dust, we know what day we're going to pass through it, and you go through, and there it is. Bang. You see all the dust particles hitting the Earth. And they're always at the same time, I mean, the same date. Perseus shower is an example of one. Okay, now here is a very exciting case. There was a comet that was broken up by passage to Jupiter. And Jupiter then, it took the comet and just shattered it into multiple pieces, and then the pieces orbited in a different orbit and came in and hit Jupiter. So here are pictures taken with a ground-based telescope that show where the comet has hit. 1, 2, 3, 4, bang. I don't know what this is. Okay, it went down and hit the comet. Let me show you another picture of that. This was a collision, 94. The comet was known as Shoemaker-Levy 9. It was about 10 kilometers in distance. It broke into 20 or more pieces. All right. And all right, so we could study the energy released by the comet, and it was quite a lot of energy. Here's the view from a moon. Okay. This is the comet Kohoutek, and it was broken into 20 pieces by Jupiter, and then it all 20 pieces in turn rammed Jupiter. And it was very pretty, very interesting. Okay, note that every one of the pieces has a tail behind it. The sun is over here, casting a shadow on the planet. And it hit the south pole of the planet and made some pretty viewing. Okay, here is another view. This is Jupiter afterwards. This is where they struck. Now, these spots were holes in the clouds. It just dug holes in the clouds. Each hole is, about the size of the Earth, rammed it through, and the holes didn't stay. The clouds are just a formation in the atmosphere, and so in a little while, they filled in again. All right, now this was something we happen to see, but it obviously has occurred. There's no reason it would not have occurred in the past. So this is an example of what can happen. Okay, and that's the view seen by the Hubble Space Telescope, and another view of it. Okay, here is a picture of Halley, and this was a close-up view taken by a satellite that went right up to Halley and tried to take pictures of it and the other material in it. The dust showering off of this comet over toward the camera was a problem. It bounced. The camera was pitted by the dust falling on it, but they still managed to get this picture. Now, one thing is that the comet has within it, it has so much gas is blowing off. It's acting like a rocket. So a rocket engine is on the comet, making it. And rocket engines, of course, change the orbit of what the satellite had. So the rockets make the comets have a different orbit than would be given by Kepler's laws. And with that change in orbit, we're a little uncertain how to calculate where it will be. But the rocket is irregular, and that causes it. Otherwise, it would be about the same. Okay. Now, here's a beautiful picture. This is a series of photographs of a comet relative to the background. Of course, the comets are close in our solar system. The background is lined up here, and you can see the comet is moving relative to it. All right, it's very close, and it moves, and you can see it easily move in one telescope in a view like this. Any questions on that? All right. Now, let's talk about collisions with the Earth. Comets hit the Earth as well as anything else. Okay. Now, Earth crossing, these Apollo asteroids that come in closer than the Earth's orbit will eventually hit us. Somehow, they're going to hit us. And what does that do? Okay. It's random. Something's going to happen. That first comet I showed, Barringer crater, is 1.2 kilometers across, and it was thought to be a 100-meter size meteorite. It was struck 50,000 years ago. Okay, now another event is known as the Tunguska event, and it occurred in remote Siberia in the year 1908. And this thing leveled 2,000 square kilometers of forest. Now, it is thought that the comet contained an explosion. The comet is coming in with tremendous speed, and that material can explode. I mean, it may. And so you want to know how much the explosion was. The comet was, it is equivalent to 15 megatons of TNT. They like to use megatons. Of course, you weren't here when the United States and the Soviet Union were sending off those goddamn nuclear weapons all the time underground, and they would say how many megatons or fractions of a megaton. Means million tons, by the way. Million pounds, a million tons of TNT. Well, that's a ridiculous amount of stuff, right? And the energy, a megaton, is equivalent to an energy of 4.4 10 to the 16th joules. That's a lot. All right, so, I mean, you can't relate what that is, but that is a lot of energy, trust me. All right, here, let me see. Here is Tunguska. This is what the whole area looked like. It leveled a forest like this for 2,000 square kilometers. Now, it left no crater at all. The comet was probably mostly water ice. It just came into the atmosphere at a tremendous speed. It finally melted and it blew up. All right, and what we think it was is a meteorite when making a hell of a mess. Now, that's one idea. Other people have their own theories, like a passing intelligent spaceship that blew up. But we haven't seen any remnants of the people from space. Lots of wacko theories are out there. You can look up and find all types of them. I'm sure you can find them on the line, and they'll tell you what really happened in Tunguska. Okay. All right, but now the event. All right, we know right now we can find 140 craters on the Earth. 140. And they're thought to be many more, but we don't see them. And we have one collision in a million years of 1 million megatons. And the small blasts, like the Tunguska meteorite, should occur roughly every 300 years. All right, now, we can see the bigger meteor, the rocks in space. We can see them when they're about 1 kilometer and larger. A kilometer-sized rock can be observed by a telescope, and you could warn the people that, oh, by the way, there's going to be a massive meteor strike tomorrow, and everybody's going to die. Okay. All right, now here is this. I don't know if I believe this, but this is the statement that you're statistically as likely to die from a cosmic collision as you are from an airplane crash. Okay, and we'll see what that means in just a minute. Okay, all right, so here's Tunguska. And here is a smaller event. This rock fell from space and dented this car. It looks like a 50s Studebaker or something or other. Okay, so the event, a chunk of a large meteorite, a large asteroid. And this is, they think, was a piece of the asteroid belt that suffered a collision. The two big asteroids came together, suffered and banged, and a rock was ejected from one, and it came into an orbit, and it hit the Earth. They think that was what happened here. All right, so watch out. Look, you know, these things may hit you, or at least hit your car. Here is where the meteorites are. 140 that are known around the globe. See, there's a lot that's not known here because it's all under snow and ice. A lot not known in the Amazon because that's too hard to search as well. But it's, you know, in a desert area, you can search better. Meteor crater, the one in Barringer, is over here. This is a beautiful view. Look at this lovely view. Here is a crater. What's that thing? Manakugas, or something or other. That's in Canada, obviously, and that's a beautiful crater. That is 200 million years ago. Okay? Up there, just north of Vermont. You know, the trouble with Earth is because of our weathering, our climate, we don't see the craters forever. They get filled in, and it loses impact. Okay, here's a picture. See that? Those, and then they burp. The sun. These are pictures of the sun taken by a spacecraft. Here it comes again. And this comet's hitting the sun. This goes in, bang. That's the end of the comets. 1, 2. Whoop. All right. So those are pretty nice. Now, suppose you had a comet striking the Earth. It was destined to strike the Earth. Okay. Now, the first question is, what's going on? Why is a comet so explosive? I mean, why? It just doesn't seem, it's just a ball of ice. What is it doing? All right, the answer is the kinetic energy. The ball is moving at speeds characteristic of the galaxy, of the solar system. And that's a speed of us in the solar system is about 30 kilometers a second as we orbit the sun. Something else that's kicked and on a different orbit will have about the same velocity, 30 kilometers a second, and it hits the Earth. Now, what does that do? So let's calculate what happens. The kinetic energy is equal to 1/2 mv squared. That's the basic idea of how the kinetic energy works. Now, that means the kinetic energy per kilogram, divide by m squared here, divide by m here, and you get kinetic energy per kilogram is v squared over 2. Okay? Now, it turns out that if the object has a velocity of 6.3, then the kinetic energy per kilogram is equivalent to that of TNT. So I take a gram here, and I throw it at the Earth at that high speed, 6.3 kilograms, and it hits the Earth and bang. Now, what is the speed of light? A speed of sound on the Earth's surface? What did I ask you? What was the speed you calculated? Problem set 6 or problem set 5? Who remembers that number? Typical molecule of oxygen, what was it, a half meter per second? Yeah. All right. So these are molecules moving in at least 10 times the speed of oxygen. It comes in fast, bang. All right, and that has an impact. So the kinetic energy comes in really hard, and that's only 6 kilometers, but the real speed is more like 30 kilometers. And so in the speed, the kinetic energy per gram goes as the velocity squared. So it comes in at 5 times that the velocity is instead of 6, it's 30. So it has 25 times the power of TNT per gram, and it causes a big explosion. The energy is conserved, and that energy of kinetic energy goes into heat after it hits the Earth. Okay, so, all right, a comet of 10 kilometers, asteroid of 10 kilometers, density of 1 gram per cubic centimeter, is the typical density of a comet that's made of ice. After all, ice is a gram per cubic centimeter. And the area, the volume, is such that this radius and this density works out to 5 × 10⁻⁴ kilograms. And the kinetic energy of kinetic energy of the entire assemblage is 10 to the 7th megatons. So that is to say, you don't want to be there when they strike. It'll make chaos. All right, this will kill off civilization, and yet they are expected 30 million years ago. Now, what will this thing do? It'll generate a gigantic tsunami. This thing comes in, and imagine what it does, hits the ocean. It will generate a tsunami with a height of order as high as can be. It'll be the tsunami will be kilometers high. It'll have a giant wave circling the Earth from that. Pash. Now, we know that this happened. In the comet strike I'm going to tell you about, the tsunami landed, the comet struck the coast of Mexico in the water. The Gulf of Mexico had a gigantic tsunami in it and sent rocks up 500 meters on the coast of Cuba, sent rocks toward Texas, huge ways uphill in Texas. People had no idea what these rocks were doing that high off the water. They couldn't explain it, and yet it turned out to be explainable. All right, this shock wave over the Earth will cause tremendous chaos. I believe it is a shock wave of Richter scale 13. And the Richter scale, you remember, is a logarithmic scale. So Richter scale 8 is pretty bad. Richter scale 9 is horrible. And it just keeps going. Okay? It'll knock everything down. Everything goes into a forest fire from just total chaos. All right, so this will immediately destroy everything within 1,000 kilometers and turns the atmosphere into a broiler, so everybody gets broiled. Then a huge dust cloud blots out the sun, food chain, everything. You get something called nuclear winter, where the sun is completely blocked out, and there's no food growing, everybody starves, and so the only animals that survive are going to be animals that nibble off the dead dinosaurs lying nearby. That means little mice, tiny mammals, okay? and they can make it through this hard time. Okay, this is thought, more than thought to be, this is definitely the demise of the dinosaurs at the Cretaceous Tertiary boundary. Does everybody know this? Who knows what I'm talking about? Who's never heard of this? Come on, answer. I mean, have you heard? Am I telling you stuff everybody knows? Okay, fine. All right. So, all right, you know this. All right, now what is some evidence for it? And ask me questions, please. Okay, now, the guy who worked out the method of detecting this is Luis Alvarez. He was a UCB professor of physics, and he worked in this building. This is a physics building. And his son, Walter Alvarez. And they had his son, Walter, who was a professor of geology. Louis was a brilliant physicist who had the idea that the way to search for this iridium, the way to search for an unusual event is to tag or look for something that has radioactivity of a sort that we can identify. And so he said, well, you know, iridium is, and he went through the table index of elements. And he said iridium fits the bill because we can look at the iridium and we can flood it. We pump it with neutrons to activate the iridium, and then the iridium will decay with characteristic emission lines of a certain line length of certain energies. And these energies will be characteristic of iridium and nothing else. So he could see if there's iridium in a sample of soil. This is what his contribution was to this work as brilliant insight. Okay, and they had no idea where the crater was, but it had been identified just in the last 5 years, or last 10 years, I guess. Okay, and everybody should read, anybody who's interested should read this fascinating book, T-Rex and the Crater of Doom, by Walter. Have any of you looked at this? It is a wonderful book. If you're interested in science, read this book. And it tells you what happened, and the story behind this amazing discovery. Okay. Now, here it is. This is the boundary. Right here, this Cretaceous Tertiary boundary is sort of dirty clay, and it's all over the world. It's everywhere. You can see everywhere on the Earth, you can see this dirty layer, dated at 65 million years. And and this is someplace in the West, but it's found in Italy. The first findings were in Italy, in Denmark, et cetera, but now they've seen it in 30, 40 places where they've looked for it. Now, what is so unusual is that if you study the composition of the material in here, and you go up, 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 there's no iridium in it. Iridium is a rare element you've never heard of that is with the material, the irons and the nickels and all that stuff that's sunk to the center of the Earth. It all got, long time ago, it's sunk because it's heavy, and it just went down the center of the Earth. There's very little iridium on our surface. And yet, the iridium in this sample was very high. Why? Why was it high? Much higher than here and here. Why was it high? Buddy? Yeah. The comet had iridium, and it had never been differentiated into iridium in the center and no iridium on the surface. When we say there's no iridium on the Earth, we're only talking about the surface composition. We don't really see the iridium in the center of the Earth. And so, and if you took the Earth and mixed it up, you would have a higher iridium as you would measure. But here on a comet, it was not heavy enough to ever differentiate itself. The forces on nothing would push it, make it rearrange itself. And so the iridium is mixed throughout it. And the iridium came down through the comet, part of the collision, and blew up all over the place. Made a mess. It covered the entire Earth with its debris. Now, here is where we think, here it is. What I'm talking about. Here's the United States, here's Mexico, here's the Yucatan Peninsula. Anybody been there? You don't look for a crater, I presume. There are some real unusual rocks in this area. And you won't see anything that looks at all like it. It landed in the water, partly in the water, partly in the land. The water had all sorts of carbonaceous carbonites in it and looked completely like anything else, any other seabed. Okay, but here is the here's Yucatan drawn here, and here is this indentation of the comet. So it made indentation and struck here. Now they know that's the comet. They can find pieces and date it 65 million years. That's clearly it. Nothing. It can't be anything else. Okay, and here it comes. There's a comet. Now this is thanks to a photographer who was on scene. The comet comes in and strikes the Yucatan. See, you even got sound. What a fantastic photographer. Strikes the Yucatan, and then it makes one heck of a wave. Starting to make a wave. All right. This thing makes worldwide forest fires, gigantic tidal wave. The iridium goes everywhere on the Earth, and it kills the dinosaurs. Because without it, the little mice what is a little mouse going to do against a big dinosaur? That versus, tiny. I mean, it's not fair. It's not even not close to being a fair fight. But if the dinosaurs are all dead, the mice can nibble on them in order to survive the million years that the Earth is a wreck, or however long it was. It was a long time the Earth was wrecked. Okay, so that's how it worked. Amazing time. Now, a lot of people would like to be there to see this come and hit us, but it's likely to be kind of dangerous. All right, here is a chart that tells how often we get struck. Every hour of every day, there are rocks of order a meter size, a meter in diameter. And if you go down to 100 meters, that happens every million years, or here every millennium or something. If you go to 1 kilometer, it's every 100 million years or so. If you go to 10 kilometers, it is every, these things get worse and worse and worse. If we get hit by something this size, that's it. We're over with. Okay, if you, unless you want to be in a magnitude 13 earthquake, man, I think earthquake preparations are to get into a field away from anything, just because, and then lie down, strap yourself to the ground so you don't fly too far when it hits you. But then you're going to live through it. I don't think you want to do that either, because Earth is going to be hideous for a while. It's going to end our population problem. Okay. All right. So all these things can happen. Pretty neat. All right. Now, so here's a question I have. Take a question and let's answer this question. What's the best chance of killing you? Greatest chance of killing you? Red card if it's a traffic accident. Yellow card if it's random gunfire. green if it's a drowning accident, or blue, killed by an asteroid. Come on, talk to somebody before you put an answer. A whole bunch of you don't have answers up. Do you have cards? Oh, we'll have to give you some. Wait, stay afterwards. I'll give you cards. Okay? All right. Most of you seem to think it's traffic accidents. How often traffic accidents occur? 50,000 people per year. That's a lot. How many people per year? Is that 50,000 right? No, it's 10,000 per year. All right. How many people? What's the rate of death in comet strikes? Well, you think about the following. It is 30 million years, and it kills 6 billion people. All right? Yeah. So you divide one by the other. 6 billion divided by, 6 billion divided by 30 million. All right? And that is, sorry? 200 a year. All right, that's trivial. See, it doesn't matter. So you guys had the right notion. 200 a year. Nothing to it. So that's fine. Won't worry about it. It's just that it has this funny statistical distribution. You don't like the fact that 6 billion people are going to die all at once. Now, how do you take out insurance for that? Whoa, that's a hard one to estimate. You know. So yes, those are it is not the asteroid. It's other things. Whatever is higher. Okay. All right. So that's the end of planets. The end of it completely. And now we're going to move on to. I believe we move on to the sun. Actually, yeah, we talked about solar system. We didn't talk about the final thing in the solar system, the energy source that powers the whole thing, a star in the center. So I will start talking about stars on Tuesday. Today is Thursday, yes. Okay? All right, so don't worry. I'll say it again. The exam, it will closely follow my notes. It will not be as mathematical as any of the problem sets have been. You don't have to worry about bringing your calculator. And you do not have to worry about remembering formulas, because every formula you might ever need is going to be printed on the front sheet of the exam. Okay. Go to TELC next week.